not sure. I think I started recording that. I'm not positive. I tried to. The thing disappeared, so I think it's recording. Anyway, I will get started. The advancer is not working, so I'm going to have to step in front to advance this. So if I'm blocking the screen when I do that, I apologize. Okay, so what we're talking about today is we're focusing on phosphorus, transport of phosphorus from soils to surface waters. Similar issue to what you have in the Chesapeake Bay, slightly different context in the Western Lake Erie Basin. The results are the same though, algal blooms. So I'd like to talk a little bit about the differences in between the two regions, and also how we can prevent those losses in the Western Lake Erie Basin. So what is the Western Lake Erie Basin? It is it's a watershed. It encompasses most of northwestern Ohio, northeastern Indiana, and southern Michigan. Much of it drains into the Maumee River, goes into the Western Lake Erie. And the land use of it is dominantly agricultural, which is why I'm here talking to you about it today, right? And there's a few pockets of some developed areas, Toledo being one of the most notable one. And of course, we have issues in the Western Lake Erie Basin with algal blooms. Some algal blooms have been so severe that you can see them from satellite imagery. And one in 2014 was so bad that it shut down the Toledo drinking water plant. And the issue is phosphorus transport. Phosphorus being the most limiting agent with eutrophication. And before we get into discussion of how it's transported, I think it's important to first discuss the definition of bioavailability, because we need this nutrient for growing crops. It needs to be in solution, and to be in solution so that it can be taken up by the plant, but also that is how it is transported as well. So start out with a brief definition of effective bioavailability. So for a nutrient to be effectively bioavailable, it must be in the proper chemical form for uptake. It must be dissolved in solution, and it must be in the vicinity of the plant root at the time of uptake. Thank you. It is, we need to keep in mind that nutrients are taken up by plants and organisms in solution, not directly from the soil. Yeah, it doesn't.
It's not the batteries.
Not the batteries. That's all right. I can improvise. It's not taken up directly from soil, how we sometimes we think of it that way. So we consider our kind of a very generic model of nutrient uptake. We have our soil as our warehouse for nutrients, and of those we have two pools. We have the labile pool and the non-labile pool, and those two pools, they're in equilibrium with each other, and they supply the nutrient in solution. All right, and once it's in solution, the plant can take it up. It's bioavailable. But once it's in solution, problem is that it's also vulnerable for transport. So again, nutrient uptake occurs in solution. That's not only true for crops, but that's true for aquatic ecosystems, for all the organisms, plants, algae, things growing there as well. In soil solution, the most common forms of nutrients are nitrate ammonium, mostly nitrate in soils, and phosphorus. It's some protonated form of phosphate. Again, nutrients got to be in solution to be taken up by an organism, but once they're in solution, it's a double-edged sword, because now you can lose them. We can lose them either as when they're dissolved, wherever the water flows, again in the forms of nitrate, ammonium, or phosphate. We have particulate losses of nutrients as well, and that is the nutrients that are bound directly to a sediment. And when you lose that sediment through erosion, any nutrients that are attached to it, you lose it as well. And specifically of phosphorus, we consider the phosphorus loss to Lake Erie. We consider two main sources, point source and non-point source. 1960s and the 70s, Lake Erie was in really bad shape. We were loading it up pretty heavy with phosphorus, total phosphorus. So this is all forms of phosphorus, whether it's dissolved or particulate phosphorus. Again, particulate is that phosphorus that's bound directly on the particles. 70s, we're loading it up big time. Then we have the Clean Water Act. We get all kinds of wastewater treatment plants built to prevent the loss, reduces the point loss. And ever since then, our total phosphorus losses to the basin, including both point and non-point sources, has been pretty good. You can see in the past 20 years, total phosphorus losses has not changed very much. However, look at the dissolved phosphorus losses. So total is particulate plus dissolved. We see a decrease in dissolved phosphorus with time, but then starting in the early 90s and continuing now, we see an increase in dissolved phosphorus. So the total loading is the same, but a greater percentage of it is in the dissolved form, which is bioavailable. It's more effectively bioavailable. Again, it's in solution, that dissolved phosphorus in solution. An organism could immediately take it up in an aquatic ecosystem and be very explosive, cause an algal bloom. That's not necessarily true for particulate phosphorus. You know, depending on the conditions, depending on how much phosphorus is on that sediment, the mineralogical nature of that sediment, some sediments may release that phosphorus. Other sediments may not release that phosphorus. It may actually absorb phosphorus from the water column. So from that regard, dissolved phosphorus is a much more potent eutrophication agent than particulate phosphorus. And it is that dissolved phosphorus is what's given us problems now in the Western Lake Erie Basin. We're losing more dissolved phosphorus even though the total phosphorus has stayed the same. And it hits that water body and this happens. This is from 2014. This was a bloom that was so bad that it shut down the Toledo drinking water plant for a week. And you can see with time, just use the pointer. With time, we see our algal blooms have also been increasing, the severity of the blooms. Here you see in 2016, last year, it wasn't nearly as bad, and everyone thought, oh, look, we solved the problem. No more eutrophication problems in Lake Erie, we kicked it. But in reality, it was 2016, it didn't rain very much. So you can't transport nutrients without flow. You got to have flow. So no, we have not solved the problem. So let's contrast the nutrient needs of crop systems versus aquatic systems. And it helps to paint the picture of why we have this issue. Only small amounts of dissolved phosphorus can cause problems in those systems. Concentrations as low as 0.11 milligrams per liter, and even less of dissolved phosphorus can cause microcystis to grow. That's what shut down the Toledo plant. But on the other hand, agricultural crops need 0.02 to 1.6 milligrams per liter, depending on the crop. Similar for nitrate. Crops need 40 to 470 milligrams per liter of nitrate in solution. Again, we're talking solution concentrations, not soil. We need a lot in solution to get reach maximum growth potential. But however, nitrogen around greater than 45 milligrams per liter is considered hazardous for drinking water. So essentially, we want our cake. We want to have our cake and we want to eat it too. In other words, we want nutrients in solution for the plant. We want them to be in solution because they're bioavailable. The plants can take it up, reach optimum yield. But we don't want them in solution to be transported. All right, so we want a lot of it in agricultural soil solutions, but very little concentrations in the surface waters. It's a paradox. In other words, we want blue waters, we want green fields. So how do we manage for achieving both? Now at this point, I'm going to take a little trajectory here and talk about the nature of the nutrients and contrast nitrogen and phosphorus. In order to best manage these things, the more we understand what they are, their essence, the nature of those nutrients, the better we can manage them. So, first thing we consider Liebig's law of the minimum in agronomic principles, right? Liebig's law of the minimum says that all nutrients in theory are equal, right? What's that mean? Well, if you're deficient in any nutrient, no matter what it is, might be a micronutrient, might be a macronutrient. If you're deficient in it, you're equally screwed in not achieving maximum yield, right? So in that regard, they're equal. But equal does not mean the same. Those nutrients are not the same, but they are equal. We say the same thing about a hen and a rooster. They're equal with regard to their chickenness, right? But you cannot expect a rooster to fulfill the function of a hen and vice versa. They're different. The equal does not mean the same. So nitrogen, you can't expect, for example, you can say lime. You can expect lime to do the same thing as gypsum and vice versa. Same thing with nitrogen and phosphorus. So how are they different? This is where I like to invoke a little philosophy, because in science we tend to look things a little bit more narrow and restrict ourselves. First of all, we forget that science actually falls under the umbrella of philosophy. And we tend to restrict our view as everything is being cause and effect. In reality, there are 5 causes from Aristotle, right? So those of you who took philosophy before 1990 probably actually know this, right? You've got structural cause, material cause, formal, efficient, and final cause. Efficient cause is cause and effect. As scientists, that's mostly all we look at. Biologists, they recognize this. They tend to consider the nature of these things. They consider the other causes, other types of causes. The essence, the nature, the structure of these things, what they are, what their purpose is. So we have Aristotle to thank for that, which was forgotten for about 1,000 years. Imagine that, 1,000 years this is forgotten, until rediscovered by Thomas Aquinas, who then perfected this and have our understanding as we know it today. So that being said, what is the nature, what is the essence of nitrogen and phosphorus? Knowing this can help us in our management. Briefly, let's look at the electron shell configuration of nitrogen and phosphorus. They look very similar initially, right? You got nitrogen, look, they both got 5 outer shell electrons, right? 1, 2, 3, 4, 5, count them. They both form oxyanions, nitrate, NO3, phosphate, PO4. Look pretty similar, but their electronegativity is different. Nitrogen is a lot more electronegative than phosphate. So I'll spare you the details, but that makes a big difference on how those electrons are shared with the oxygens, which then has a major impact on their behavior and how we should manage them. The bottom line is that because of this difference, nitrogen is extremely dynamic. Nitrogen doesn't like to stick to things, and essentially what it means is when you apply nitrogen, the second you put it out there, it's on its way to being lost. It's on its way to being lost either through leaching or in some form of a gas if it's not taken up by a crop. So with nitrogen, if you don't lose it, you lose it. Very different from the nature of phosphorus. Phosphorus binds very strongly to soils. In fact, most of the phosphorus that we apply to a soil is not going to be taken up by the plant, at least anytime soon, and it's also not going to dissolve back into solution. A lot of it is irreversibly held. Totally opposite of nitrogen. So because of that, we have phosphorus, we can develop these legacy phosphorus soils, where the soils, you can actually build up phosphorus concentrations in your soils. There's no such thing as legacy nitrogen. Right? We don't necessarily build up nitrogen in our soils. Every year you get, for the most part, a clean slate in nitrogen. Not true with phosphorus. Phosphorus hangs around, again, because of its difference in its nature. Here's an example. This is Maryland data. They artificially built up soils all the way up to 600 milligrams per kilogram of malic 3 phosphorus. Cut off phosphorus applications. Put it in a corn, wheat, beans rotation and measure drawdown. Harvest it, take it off, and measured how long it took for the phosphorus levels to go down, and it takes decades. I think the recently published paper, I think it was with malic 3 levels of around 400, it was taken, if I remember correctly, somewhere between like estimated 20 to 40 years to come back down to agronomic optimum P levels. And the problem is, during that time, every time you get a flow event, you're losing a little bit of dissolved phosphorus, just a tiny bit, which isn't a big deal agronomically. You're not losing that much. In the hot spots, you're losing half a pound of dissolved P per acre per year. That's nothing. That's 30 cents per acre. Big deal. But to an aquatic system, it's devastating. So that being said, how is phosphorus being lost to the Western Lake Erie Basin? One thing to keep in mind that's different from, mostly different from the Chesapeake Bay watershed is that Western Lake Erie Basin, we are dominantly artificially drained with tile drains. You see the density of tile drainage in the United States, and those hot, right up there in the basin, we're among the highest density, and we're putting in more tile drains. And some people in that region will say tile drains are Satan. That's not necessarily true. So we've got an area with heavy tile drains that drain into ditches. We have several watersheds we monitor in northern Indiana and also Ohio, monitoring surface runoff as well. I'll share with you some of that data. The first thing I'll compare is the phosphorus concentrations, differentiate from loads. Phosphorus concentrations lost from the runoff, surface losses here, versus tile drains, dissolved P and also total P losses. It's interesting to note is that we have higher concentrations of dissolved phosphorus lost in runoff, not tile drains. Lower concentrations in tile drains. Well, you think about it, should make sense. The water percolating through the soil profile, you've got a lot of contact of that dissolved phosphorus with the soil before it hits a tile drain. So you expect that you'd have lower concentrations. But that doesn't necessarily mean you have less loads, because we need to consider the total amount of water that's being lost. And when we consider that, much of the water, this is for Ohio particularly, much of that water goes through a tile drain before it hits the Maumee River. It turns out that 73% of the dissolved phosphorus load in Ohio in the Western Lake Erie Basin is coming through tile drains. Even though the concentration is lower than runoff, the load is higher simply because that's where the water's going, and it moves with the water. Similarly, in Indiana, it's not quite as much. About 56% of the discharge of our water is from tile drains to Lake Erie, and about nearly half of our load of dissolved phosphorus is from tile drains. The other half is from surface runoff. Okay, so how's it lost? We know it's going through tile drains. We also, a very large chunk of it's coming through tile drains, some of it through surface runoff. Two main categories of non-point phosphorus transport: incidental phosphorus losses and soil loss, or that loss of phosphorus from legacy P soils. So phosphorus lost directly from recently applied manure and fertilizer, we call that incidental losses. So imagine you go out and you apply your manure, or it can be chemical fertilizer, and it's not incorporated, it's highly vulnerable. You get a rainfall event soon after, and it's highly soluble, it transports it right off site. You have a catastrophic incidental loss. That's different from legacy phosphorus losses, where the phosphorus is lost from the soil, not from the recently applied fertilizer. There's kind of a gradient there, there's a line there somewhere. But again, your soils that are built up, they slowly leak out phosphorus. You don't have these huge catastrophic losses like you do with incidental phosphorus losses. They are much more frequent, but they're much smaller. So it's always leaking a little bit all the time, and it's cumulative, whereas the incidental losses, it's much less frequent, but when it happens, it's a huge load when it happens. So first, let's talk about the incidental losses. When we consider incidental loss of phosphorus, we need to consider phosphorus solubility with time after a fertilizer application. And this can be fertilizer or manure, but initially, when we first apply our fertilizer, it's 100% soluble. It's nearly 100% soluble, and it increases the soil extractable pool. And then with time, that phosphorus, that fertilizer phosphorus, the solubility decreases with time as it reacts with the soil. So if you get a rainfall event somewhere up in this window early on, you're going to have a lot of incidental phosphorus losses. you're going to get a huge slug of dissolved phosphorus you're going to lose directly from that fertilizer. Now imagine if you don't incorporate it. Let's say this hypothetically with no incorporation of your fertilizer. So now, with no incorporation, your soluble phosphorus pool, it stays elevated for a longer period of time. Now you've got a greater window of time that you can lose that phosphorus if you get a flow event that occurs then. Thank you. So that makes the timing of phosphorus application and application method extremely important for minimizing incidental losses. We have a lot of incidental phosphorus loss in the Western Lake Erie Basin because our traditional application method is broadcasting. When you broadcast the fertilizer, you minimize the contact between the soil and the fertilizer. So you don't pull that solubility down into the soil very quickly. It stays highly soluble for a long time. To solve that problem, well, you want to maximize soil fertilizer contact, decrease that soluble P level, move that fertilizer phosphorus pool into the soil pool. You can do that by either incorporating it, banding it, injecting it, using liquid applications, anything. Just get that phosphorus into the ground so it can react with the soil. This is made worse in our situation because our fertilizer the timing of our fertilizer spreading occurs mostly from November to April. So we apply it on the surface, we leave it at the surface and don't incorporate it, and it just sits there at the surface during a time period when we get rainfall, and that rainfall is it's being lost as straight to the tile drain and as runoff because plants aren't taking up much water during that time period, right? And if the plants aren't taking it up, then you're going to lose that water. And if you're losing water, it's taking nutrients with it. So it's a double whammy. We have this highly soluble nutrient source right at the surface, and we're losing all our water at the same time to transport those nutrients. So again, those two things together is really, really hurting us. Oftentimes they'll apply the fertilizer, leave it on the surface, and they won't incorporate it for, it might be weeks, it could be months. So you've got this huge window where if you get a flow event, you're losing. It's going to stay soluble for a very long time because you didn't incorporate it. And, well, it gets worse. First, let me give you an example of this. Here's a hydrograph. This is for Honey Creek for some series of storm events. And on the bottom, we have the phosphorus concentrations. Now the arrows here that pop up, this coincides when the custom fertilizer applications were made. Look at the big spikes when they go in the field and apply it, surface apply it, and then you get a flow event after. You get these huge losses of dissolved phosphorus. This problem gets even worse when you consider that we have a lot of preferential flow paths in our soils there because a lot of them are very heavy clays. So it's not uncommon to see cracks like this form on the surface in these channels that'll go from the surface all the way to the tile drain, short-circuiting the soil. So here's a fertilizer broadcast application. You got your prills right at the surface, highly, highly soluble, 100% soluble, right next to a crack that could be directly connected to a tile drain. Worst case scenario, that makes it much worse. Now if you till it, you can break up a lot of these preferential flow paths not only incorporate the fertilizer and reduce its solubility, but you break up the physical flow paths as well. If it's not tilled, you don't break those up. I can show you an example of that here in some data coming up here. Give you an example of just how devastating this preferential flow path can be. Using isotopes, we could monitor the ratio of the water in the tile drain that is new water, event water, versus old water, soil water. So you get a rainfall event, and some of that water that comes down in rain, some of it, in ideal situations, it goes into the soil, becomes soil water, and it pushes the other soil water, piston flow, it pushes that down into the drain. But if you have preferential flow paths, that event water from the rain, it can bypass it through those preferential flow paths and go straight to the drain. we were able to measure out these isotopes. And what we found was that 26 to 69% of the discharge in the tile drains was coming from that new event water, from that rainfall. That means that what hit the surface was going straight down to the drain. And if you've got phosphorus fertilizer right at that surface, it can be catastrophic. There's an example of it in losses. We look at the impact of tillage and breaking up those preferential flow paths and reducing the solubility by maximizing contact. So here's a tilled site. Here's a no-till site. Blue lines is our discharge of flow in the tile drain. This is before applying fertilizer. Here's our phosphorus concentrations. We haven't applied any phosphorus yet. Okay, no problem. Here's our phosphorus loads. Okay, no problem. Now, let's apply fertilizer to these sites. Again, on the left, here's our tilled site. We applied fertilizer. It's tilled in. It's incorporated. You get a little bump with a flow event. Some dissolved phosphorus concentrations hit a peak. But look at it for the no-till site. Look at the spike in dissolved phosphorus concentrations hitting that tile drain. That's through those preferential flow paths. It's bypassing the soil, short-circuiting straight down to it. And you can see the same effect in the loads, in the mass of phosphorus that's reaching those tile drains and going straight out. Another issue, another thing you hear people talk about in the Western Lake Erie Basin is the phosphorus source. That is chemical fertilizer versus manure or less soluble sources. You know, they'll do studies like this. They'll apply it to the surface. This was surface application, then they have runoff. And they say, hey, look, these highly soluble sources, triple superphosphate and all these chemical fertilizers, they're so soluble, you apply them at the surface, we're losing it. You know, obviously they're not getting mixed into the soil and solubility decrease, so they'll say, well, here's the solution. They'll say the problem is these chemical fertilizers are unsustainable. We need slow release fertilizers. That's what they'll say. Is that, knowing what you know about the nature of phosphorus and nitrogen, does that make any sense? We already have a perfectly suited slow release phosphorus fertilizer. It's called the soil, and it's perfect. It works great. You just have to incorporate your fertilizer into the soil to convert it from a fertilizer phosphorus pool into a soil pool. The soil phosphorus pool behaves as a slow release fertilizer because of the nature of phosphorus. Binds to the soil. Nitrogen, you want to talk about slow release fertilizers, nitrogen, that makes perfect sense. Nitrogen doesn't stick to the soil. Once you put it out there, it's off to the races if it's not taken up by the plant. So nitrogen makes a lot of sense to use slow release fertilizer. Makes zero sense for phosphorus. We have the soil. You just have to get it in the soil. So the other main way in which phosphorus is lost, so we have incidental losses. Second, legacy P loss. That's the more frequent, smaller, less catastrophic, but more frequent losses of dissolved phosphorus. Legacy phosphorus, it's not as leaky compared to nitrogen, but it does add up. That tiny bit of phosphorus, when those soils get built up, you lose that dissolved phosphorus. That small amount, half a pound of dissolved phosphorus per acre per year, is enough to cause big eutrophication problems. So how do these soils get built up in soil test phosphorus? Quite simply, application of phosphorus beyond the need of the plants year after year after year. And you can do this a lot of different, you can do this applying phosphorus in any form. It doesn't matter if it's compost, manure, chemical fertilizer, food waste, whatever. It can be any form. But it tends to happen more frequently with CAFOs because of the regional distribution imbalance of phosphorus. In other words, they tend to have a higher concentration of phosphorus imported to those farms that stay there. So it's much, regionally, they're knocking that phosphorus balance out of whack. So big issue in the Chesapeake Bay region, right? We have CAFOs, and if you're not careful in management, those soils can get built up very high and become legacy sources. And we do have some of that in the Western Lake Erie Basin as well. Again, you can build up a soil with any type of, build up legacy P with any type of phosphorus form. Problem is you get your soil malic 3 levels built up, and the amount of dissolved phosphorus you lose in runoff and drainage increases with it, and that's sustained for decades. If you recall, it's going to take decades for those soil P levels to go down. So every time it rains, or a flow event at least, you lose some. Very different from nitrogen transport. You look at this figure we have on the top, nitrogen concentrations lost, and on the bottom, phosphorus. We have edge of field tile drain concentrations. This drain goes into the Portage River, and that drains into the Maumee River. Okay? So we look at nitrogen first. You see some effect of a storm size in the hydrograph in the background, those peaks. But for the most part, when nitrogen is applied, as soon as you apply it, if it's not taken up by the crop, it's on its way to being lost. You're losing it. All right? You can see a little bit of changes with the peaks in the hydrograph, but again, it's on its way. Nitrogen is not soil buffered. Again, we consider the difference in the essence between phosphorus and nitrogen. Phosphorus, remember, because of the way it's held by the soil, we see those differences in how it's lost. It's flashy. It tends to be lost mostly in large events. Look at the phosphorus concentrations. They follow the hydrograph perfectly because it's soil buffered. Legacy phosphorus it's a soil buffering process as it supplies it to the solution. Not true with nitrogen. So again, how do we build up those soils with phosphorus? Just applying more phosphorus than the plant needs year after year after year, regardless of phosphorus source, regardless of the location or the land use. Doesn't matter if it's ag, if it's urban, if it's a golf course, it's horticultural. Doesn't matter. So not only can soils get built up, become legacy sources, sediments can as well. So a lot of these sediments, these ditches and reservoirs that have been lost from these landscapes, they accumulate in these ditches, and they can slowly release dissolved phosphorus for decades as well. So how do we prevent soils from becoming legacy sources? Well, the short answer is good nutrient management. Having a good nutrient balance between crop uptake and what we apply. However, there are some challenges to that with fertility recommendations. We rely on good fertility recommendations. And we consider our soil test recommendations are based on 0 to 6 inch samples. But now we have no-till. That's not very representative of no-till conditions. Not only that, but our calibrations for soil phosphorus fertility was based on calibrations done 30 to 50 years ago. And they had, at that time, no consideration of differences in soil type or conditions. Plus, we have different crop varieties now. At that time, it was one size fits all. And it worked. It worked fine. It got you in the ballpark. It was all right. But it's a different time now, different economically, and we also have issues with water quality. So point is that we're going to be a lot more precise with our phosphorus applications. I mentioned no-till. Briefly, Western Lake Erie Basin. Now, we don't have true no-till. We have very little true no-till, or I'll call it never-till there. Most of it's rotational no-till. But even with that rotational no-till, we still see stratification of phosphorus more concentrated in that top 2 inches of the soil. How is that going to impact our recommendations if they're all based on 0 to 6 inch samples? Here's some data from when I was at Oklahoma State. Give an example of fertility recommendations and how there's a lot of slack with them. A lot of room for improvement. This is winter wheat yield. This is a soil that had 5 milligrams per kilogram of malic 3 phosphorus, very low in phosphorus, right? So, hey, you got to fertilize this, right? Soil testing lab said we need to apply 83 kilograms of P2O5 per hectare for this to reach optimum yield. All right? That's the black bar. That's what we did. We also had a check plot with 0 P applied, and we have a range of other P application rates. We measure our yield. Here's our check plot for reference. No significant differences in yield. Super low P soil. We applied lots of phosphorus, exactly what it said. We should have a huge response in yield. No response. And you see a lot of people mention this throughout the country. They observe this. Why? This is where I'm kind of shifting my career to at this point into my goal is to, over the next 5 to 10 years, to improve and make phosphorus fertility recommendations more precise, and potassium as well. Also consider shortcomings with certain soil tests like Mehlich 3. Here's a field where the total phosphorus in the soil was the same. We didn't change it. We adjusted the pH of the field and let it equilibrate for several years and measure Mehlich 3. So the total phosphorus is the same, but look, pH 5, Mehlich 3 says we have a lot more crop available phosphorus compared to pH 7. That seem right? No, that's not right. Because we know, we measure what's in solution. Again, that's what plants take up, is what's in solution. This is water-soluble P. It's indeed the opposite. So Mehlich 3 is lying to us under certain pH conditions. So Mehlich 3 can be abused. It's valid only within a certain pH range. We consider how these phosphorus recommendations were created. It's just a simple response to soil test level. Here's your Mehlich 3 or Bray or Olson or whatever it happens to be, and we measure yield, relative yield, and as we increase the soil nutrient level, the yield increases till we hit some optimum, right? And right there, or right here I should say, that's our soil test level where that's our target, right? That's how it's always shown. You guys have seen this before, right? Everybody's seen this. In reality, you know what it really looks like? Looks like that. If you ever looked at the actual raw data, it's a mess. So, they strike the line in the middle and call everything good, and it gets you in the ballpark, right? And it served us well for decades. But, depending on the soils and the conditions, maybe yours looks like that. Maybe the response is something like this. Maybe it's this. Maybe it's that. So depending on what you've got, you may be over-applying phosphorus in some cases, or you may be under-applying. So the same thing is true with potassium. A lot of room to make that more precise. We have all these precision application technology, and they're all, for phosphorus, they're all worthless without precise recommendations. So preventing legacy phosphorus, we need good nutrient management, which also requires good fertility recommendations. If you're a CAFO, if you're not a CAFO, then achieving that balance is fairly easy. It can be more challenging if you are a CAFO, if you're importing more phosphorus than what you're exporting. But if you do develop legacy phosphorus, then the options are you have to contain it. You need to contain it, and you need to remediate it. So contain it, I mean prevent the phosphorus from leaving the site. We do this a lot in the Western Lake Erie Basin, and you do this some here too with flow control structures on our tile drains. In other words, we'll kind of dam that tile drain a little bit and raise the water table in the field and reduce the volume of water that leaves the site. By reducing the volume of water, you reduce the load of phosphorus. Phosphorus can't reach Lake Erie if the water doesn't get there. Likewise, we can use vegetative filter strips to reduce the flow, reaching the surface water, reaching the ditches. But all that does is contain it. It helps a lot. It contains the problem, but it doesn't fix it. It doesn't take the root of the problem away. 100% containment is not possible. Remember, those ditches and those tile drains are there for a reason, right? Agriculture wouldn't be possible without it. So we can't contain all that water all the time. So containment is helpful, but it's kind of like a Band-Aid. So to get at the root of the problem, for legacy phosphorus at least, now we're back to talking about if you're not able to prevent its formation and we contain it, then the next thing is get to the root of the problem and remediate it. Actually reduce the legacy phosphorus. I mentioned this earlier, ceasing phosphorus applications. Uptake the phosphorus, draw down through a crop, harvest the crop, get it out of the watershed, and draw those soil levels down. Again, the problem is that can take decades if your soil test P levels are really high. And during that time, every time you get a flow of it, you're losing a little bit of dissolved phosphorus. So it's a short-term solution. I don't know if any of you saw the talk I gave this morning. We have phosphorus removal structures to filter out that phosphorus during that time period before it reaches the surface water body. And they're just basically large landscape scale filters that absorb phosphorus with filter media. And I'm not going to talk much about that, but they can look a lot of different ways. We can filter out tile drainage and runoff, and we can build them all different kinds of ways in agriculture and urban landscapes, and ditches, whatever. Okay, so in summary, there is no silver bullet explanation for the dissolved phosphorus increase to Lake Erie. We know the dissolved phosphorus increases to Lake Erie is what's causing the problem with eutrophication, but exactly what the source is, okay, we know we've got a lot of incidental losses. We've got legacy phosphorus losses, but I can't stand here and tell you, hey, 80% of it's from incidental losses, 20% is from legacy P. We don't know. They're obviously both contributing. We try to reduce these incidental losses with, it's low-hanging fruit. We can stop incidental losses fairly easily by timing of applications of fertilizer and our application methods. And for legacy P, the easiest thing to do is prevent it from occurring. All right, with that, I will take any questions that you have. Okay. The question is why do we see that inverse relationship between Malic 3 phosphorus solubility and pH? It ultimately comes down to the chemistry of the Malic 3 solution itself and what it was designed for. At a low pH, Malic 3 is more excessively, it has a lot of fluoride in it. It's excessively extracting aluminum phosphates, which are not necessarily going to provide a plain available source. There's other reasons as well, but that's the biggest one with the aluminum phosphates. It's over extracting a pool that's not truly available. I have a paper that's hopefully going to be published soon on that, where I go through the Malic 3 solution and examine all the chemistry of it, all the different components of Malic 3, and examine how it removes P at different pH levels, explaining it in detail if you ever have any problems sleeping at night. Hopefully it'll be published soon, but it's a good question. And the problem is it extracts a lot of it at low pH, over extracts it because it's more soluble with that fluoride, but it's not soluble in water. And again, if it can't get into water, a plant can't take it up. We go back to our definition of effective bioavailability. So Malic 3, it's not a very, don't use it at a pH below about 5.5. Yes, sir.
The one thing that's going through my mind, you're working in one of your answers is to work the soil, work the fertilizer into the system.
Incorporate it.
So
Yeah.
you're no longer no-tilling, so therefore you're depending on the slope of the land, this may be fairly flat. You also have erosion issues with that soil coming on.
Right.
So it looks like a lot of buffer strips and a lot of minimum till.
Yeah. Okay, so yeah, it's a good point. There's double-edged sword. We incorporate it. We incorporate the fertilizer to reduce dissolved P losses. We don't want to disturb it so much that we have a lot of sediment losses through erosion, right? And that's an issue. So the idea, the solution is to be able to incorporate it without having to disturb it too much. Banding without having to till everything up completely, because you make a good point. If we do get too crazy on the incorporation, well, guess what? Now we just increased our particulate phosphorus losses. Even though our dissolved losses may have gone down, we'll increase our particulate losses. So you want to get it incorporated. Ideally, what we're finding is that liquid application is better, because a liquid naturally incorporates itself without having to disturb the soil. I don't know. I'm sorry. I don't know anything about the cost on that. But I know there's a lot of ag engineers working on equipment to be able to incorporate an appreciable amount of phosphorus. It's going to take more than just a starter band. Okay, it's going to take more than a starter band. So that's going to require different equipment.
But the amount of phosphorus that's required, I mean, a 2x2 row placement.
Right. It's not enough in a lot of those soils. you need to apply more. So that's why they're working on developing newer equipment to apply more in bands.
So incorporation is one, timing is the other.
Yep.
And you hear a lot about the upper Mississippi River Basin with fall application of phosphorus.
Yep.
Don't do it.
Don't do it. The longer you leave that phosphorus out there at a time when there's more flow, consider that figure I showed. You've got a greater window. You've got a greater window for losing that phosphorus. Apply it. You want to apply it when there's going to be less, when less of that water, rainfall, is going to be lost to a tile drain or to runoff. So applying it in November and not incorporating it and leaving it there is the worst possible thing you can do. If you incorporate it, apply it in November and incorporate it, you're okay.
Put a cover crop on top of it.
Cover crops is something that I personally have not done research on. There's some of my colleagues at Purdue are. And for nitrogen, the cover crops, they're seeing a very good response with in preventing nitrogen losses. For dissolved phosphorus, they're not seeing much of a benefit of the cover crop. And again, that's part of the differences in the nature of the difference of nitrogen losses versus phosphorus. But still a lot of work to be done on the impact of cover crops on nutrient losses and soil quality in general.
I just had a couple questions on malic-3 phosphorus. So do you know what proportion of malic-3 is actually utilized by plants? I'll let you answer that before.
I give you the short answer is it depends. It's going to depend on the soil type. It's going to depend on the
Let's say sandy loam 6 pH.
Oh gosh, I can't give you, I couldn't give you a number right now. If I did, I'd be lying. I'd have to crunch some numbers, go back and look at something, but just I can tell you, well, consider that, let's just consider the percentage of malic of total, and that's not a very high percentage. You figure a lot of these soils, total phosphorus around, say, 1,000 milligrams per kilogram, malic-3 levels of around 30 or 50 milligrams per kilogram. So only a small portion of that total P is going to be bioavailable. Even smaller proportion of that malic-3 is going to be taken up by the plant. But what that percentage is offhand, I can't say.
So my second question is, which pool of phosphorus is being extracted with malic-3?
Malic-3 is getting a very large proportion of aluminum-related phosphorus.
So
and
it's not getting any iron.
Oh, it's getting iron phosphorus as well, and it's getting some calcium phosphates as well. That's why we don't want to use malic-3 in really high pH soils that are dominated with calcium phosphates. Then you're over extracting it the other way. In a low pH soil, it's the opposite. You're over extracting the aluminum pool. That's why ideal range for malic-3 is probably about 5.5 to 7.5. But malic-3 was designed to try and get a bit of and look, I'm not criticizing Dr. Malik. It was brilliant. He developed this test, designed it to extract a little bit of each pool, a little bit of the organic pool, a little bit of the iron pool, aluminum pool, and the calcium phosphate pool. The problem is it grabs too much of certain pools when the pH gets too low, too much of the iron and aluminum pool when the pH is too low, and too much of the calcium pool when the pH is too high, relative to what's actually going to go into solution. Creating an ideal soil test is really difficult. You want something that's going to predict what's in solution over an entire growing season. Can you imagine the challenge of that? So they've done pretty good, what he did was great. But we can tweak it, we can improve it and make it better.
So I'm looking forward to what you're working on, because that's something I'm very interested in learning more about malic and how we can tweak the test.
I'll be happy to work with you on it.
And another, I don't think we know, but we know that malic does extract an organic phosphorus pool from the soil.
Organic. Absolutely.
And we
Yes.
don't know if that pool is degraded during extraction or what happens to that pool.
Yeah, okay, so your guy obviously knows a lot about organic phosphorus, but with malic-3, you are definitely extracting extracting some organic phosphorus pools, and depending on the method that you use for measuring that extract, if you're using a colorimetric method, you're only going to get part of it. ICP, obviously, you're going to get all of it. Now, Malik 3 is just telling you what's in solution, right? Now, how much of that is going to then become plain available, because it's going to extract that phytate. Now, whether or not it's going to get cleaved and become plain available, you know, that's another issue right there. That's another story.
Or like your pH is so low, most of the your diasters will be gone, and you will think that they're actually inorganic, but they may not.
All right, yeah, we're gonna have to cut it off. Good discussion, though. All right, let's give Chad a hand.